All right. Welcome back to the Hurwitz Lab. Hey, Alan.
Hey, Craig.
I am excited for our discussion today on CounterCurrent Multiplication. And this is really a great follow-up to our first podcast on water balance and also our discussion of flow. When we talked about water balance and flow, we really focused on systems the body uses to alter permeabilities to regulate homeostasis. And our talk today is going to outline the amazing process the kidney uses to create the large driving force needed to move those big volumes of water so we don't die from dehydration. Now, I've passed my nephrology boards 2 times in the last 20 years, but I definitely think after today's discussion, I will truly be a nephrologist if we can demystify this often confusing process. Alan, I want to thank you for coming back to the lab and for helping us over the last few months and sharing your expertise on these fun and challenging topics.
Well, thanks, Craig. I mean, it's been great fun for me. I mean, I got to say, over the last couple of months, I think this is the most fun. Coming over here to do these is the most fun.
I've really enjoyed it.
We've had a good time, and we've learned a lot.
Wow.
To each other, and I think you learned a lot this week.
This has been the best review. The last few months have been one of the best reviews. I'm so ready for my third take of the boards, I think.
Yeah, but sometimes you know too much.
That is definitely true.
Right. Because I think you're going to be, I think the stuff we're trying to present, I think, is certainly, we're trying to come close to the edge of what's known, and sometimes that'll get you in trouble.
And I think the topic we picked today, which is countercurrent multiplication, is one of the most challenging topics.
It is very difficult for a lot of people, and it's one of those things that in medical school you learn it for the test,
right?
And then maybe you'll learn it for something else. And then sometimes as a nephrology fellow, it may dawn on you this stuff is important,
right?
But you don't really have the time because you get busy really fast to go into it. And so the point of this one is to take, again, another deep dive and explain the concept and lay it out, but at the same time, give the history and show that there are nuances and complexities that we still don't understand. Certainly when it comes to the inner medulla, there are still questions. And
absolutely.
It's amazing.
And so many things in the last week as we've discussed the topic a bit and reviewed articles and the stuff you sent me. I've learned so much about parts of it that I thought were the easy part, like the vasa-recta and the interplay of the blood vessels. And now I realize that there's so many pieces to this that you're going to outline for us. And I think this is going to be a really good review.
And I'm hoping also to show people, to show some analogies to things that we see in the outside world as well, because these biological systems, they appear in nature and other places.
Absolutely.
And certainly engineers either coincidentally discovered them in parallel or, took a lesson from physiology.
Yep.
But yeah, so on this first introductory slide
I
here,
got the slides up.
What we're showing is, this doesn't look like a nephron to anybody, but this is the U-shaped thing is the Loop of Henle, the thin descending limb.
Oh, do you have your pointer on? Because this will be a good one for you to be able to point.
Thin descending limb
Perfect.
here. And you'll see that, the big message of the thin descending limb is water leaves because there's Aquaporin 1 channels, and that water is going to be reabsorbed by the vasa-recta. And then, there's more and more concentration as you go down. And then less and less as you come up. So students often figure, okay, the Loop of Henle is a big waste of time.
Done. Check.
We concentrated on the way down and we diluted on the way up, and we're coming out the same way we went in. What did we get accomplished? But hopefully, the Loop of Henle is doing this because there's more nephron left, considering the collecting duct especially. And then, the system is not quite as simple because there's an interstitium here. And you will see the importance of active transport of salt. And, of course, the kidney was the first in the business of recycling.
And I think you bring up such a good point, because so many times when people do the countercurrent diagram, they don't talk, the collecting duct is missing.
Right.
And meanwhile, this is for the collecting duct.
Yeah, the collecting duct is right here.
The final hurrah.
Yeah, the collecting duct is right here.
That's it.
That's the IMCD. And I do want to say that, the kidney is so great.
Let's just leave it there. The kidney is so great.
The kidney is so great, but when the rest of the body metabolizes proteins, the waste product is urea, as we know. And then the body tells the kidney, okay, here's our garbage.
Yeah.
Take it out for us.
Yeah.
And the kidney, of course, a lot of urea in urine. That may be where the name urine comes from. But, the kidney thought to itself, this garbage that's coming down here, maybe I can use that. And so leave it to the kidney to say, I'm going to throw out your garbage, but you know what I'm going to do? I'm going to learn to transport it, and I'm going to recycle it. I'm going to find a use for it.
That's it.
You'll get a box of electronics. I don't know what this is, but I'm going to find a use for it.
That's right. We're going to make it work.
Right. So this is where we're going, and here's how we're going to start off. So again, remember that the nephron is in the business. When the GFR filtrate comes into the Bowman's space, it's got a ton of sodium in it from the ECF. And again, students are confused. Why do you dump all that stuff into Bowman's capsule just to reabsorb 99% of it?
Right.
And the reason is because the kidneys figured out a way to tie sodium reabsorption to every other process it does. And that's why every part of the nephron knows how to reabsorb sodium. And that's, of course, the basis of our diuretic therapy. Right. So, diuretic therapy targets these different sodium transporters. And we'll talk about that in a separate session called diuretics.
Yeah, I love it.
That I think I'm planning. So anyway, this just tells you that, we're going to be looking at mostly these three things here. And what's not shown in this diagram are the blood vessels. This is all tubule.
Right.
So the descending limb, the tip of the Henle loop, the thin limb ascending, the thick limb ascending, up to the macula densa. And then, we're going to be focusing on these three tubule segments, especially in the inner medulla. But you have to remember, and you'll remind us of the blood vessels that are always here.
That's it.
Okay. So countercurrent exchange. So we're talking about two different processes today, correct? We're talking about countercurrent exchange, and we're talking about countercurrent multiplication. And those are very interesting terms. Now, countercurrent exchange is something that is not unique to the kidney. It's found in many different systems in nature, the gills of fish. Mm-hmm. It's the way animals retain body heat despite having their feet in very cold water, if you're a reindeer or something like that. Okay. It's how whales retain their body heat despite swimming around in a very cold ocean. And again, you need countercurrent exchange is combined with countercurrent multiplication in the kidney. So the whole process of countercurrent systems, to me, is the exchange in the kidney, the vasa, and the multiplication that's going on in the tubules. And so it's all this, plus the interstitium, plus the complexities and the nuances of the branching blood vessels.
Wow.
Okay?
Yeah.
And then engineers have used, this for heat exchangers, of course, and we use it every day, right? When you tell us about how we set up the dialysis machine in hemo with the hemofilter.
Right, exactly. The blood goes in on one side and the dialysate goes on the other, and the blood goes through the fiber, the hollow fiber of the filter, the straws, and then the dialysate goes in the opposite direction.
And why do we take care to make sure we're doing that? Instead of running, just say, it doesn't matter.
Right. No, it maximizes the equilibrium between the two.
Right.
So
it really maximizes the not coming to equilibrium. Really.
Right. Exactly.
It's allowing diffuses.
The transport.
It maximizes the transport. Exactly.
Between the
exactly.
two. Mm-hmm.
So it's because if they ran the same way,
right,
you might lose your diffusive driving force.
Right.
Okay. So you do have to pay attention that usually the blood goes down. There's the red and the blue port, and the dialysate runs up.
Right.
So, and they run at different rates, but that's separate from the fact that they're running in different directions. So there is countercurrent exchange in a hemofilter. Okay, so this is just a table I took from a recent review that shows, these examples of countercurrent exchange, and you see, a big one is to conserve body heat. Again, temperature gradient is a temperature gradient.
Right.
It's a driving force. You don't want to give a lot of surface for loss. So you minimize the surface for loss. And I'll show you this in some pictures. The U-shaped tube with special properties is used. It's also used for other systems in the swim bladder. Our airways, our nasal passages, the way we heat up the air. Like you go outside in a cold day, mm-hmm. your lungs aren't going to like that freezing really cold. Yeah, it's going to cause bronchospasm. And in asthmatics, it does. Mm-hmm. So there's a big humidifier heating system set up in the nose, and there's lots of little countercurrent systems for that. And whether you're conserving temperature or extracting oxygen, the same kind of thing sets up. And of course here, the placenta, that's an important place, right? Placenta is between the blood supply of the mom and the baby. The man-made devices we talked about, and they've got hemodialyzers on the list there. That's good. Okay. So what do we mean when we talk about concurrent, or sometimes they say co-current exchange versus countercurrent? So the top shows concurrent or co-current And what you see there are two pipes. One is got blue cold stuff, and one's got red hot stuff. And they communicate. There can be diffusion between the two. There's a permeability between the two. And the easiest real life example of this for me is just your hot and cold faucets,
Right.
which you say is a mixing valve.
Right, exactly. Well, it's the two. This is perfect. But the part where they're talking about is where the two meet up and come out the single tube.
The single tube.
Yeah.
And so it's a very inefficient process. So what's convenient about it is we use our feedback system to our trip channels to test the water. And then we make the adjustment with our feedback. We adjust the driving forces. And then we get what we want. But it's very inefficient because we're wasting, instead of making an efficient one temperature using a good feedback system, we're basically running an air conditioner and a heater at the same time, which is not the way,
not the best way to
not
do
the
it.
best control system.
Right.
And you see on the right here that they can come to equilibrium before too long, and then there's no driving force anymore. I mean, it's a loss of efficiency. Whereas if you set things up the countercurrent way, what you get is there's always going to be, they don't come to equilibrium, and there can be conservation, and there's a short circuiting so that you can keep heat in the body or whatever you're trying to do. Okay, so let's take a couple more examples of that. Here again is the same concept. On the left is concurrent. In this particular case, it's water flow and blood flow, and you see that here by the end of the tube, you've lost 50% of what you started with. You lost 50% what you started with, but you're only having diffusion part of the way. Once they come into equilibrium,
it stops.
Whereas equilibrium is not reached in the countercurrent example, and therefore you
maximize diffusion.
It's constantly taking place over the whole surface, and that's what you want to do. So again, this just shows the same from a different paper. It shows, I think, just a little bit more of a mathematical model of what happens to flow 1 and flow 2, but the countercurrent is what you're looking for when you're trying to conserve. Okay. So here is a real life example of, let's just say this is a fin of an animal in cold water, and how it's trying to use countercurrent exchange to not lose heat to the environment. So you see here that the way the flow works is that even though this may be pretty close to freezing at the tip here, the animal, because there's shunting, there's short circuiting of heat going across here as this fluid flows down and this fluid flows up, that there's an effective keeping in of the heat.
Yeah, and it's so nicely in the other picture too, where there's those little crossover capillaries between the two.
Are we going to see that?
I love that.
Are we going to see that again?
I love that vascular bundle.
You love the vascular bundle.
I do, because I love shunting.
Yeah, so today I decided to be the tubule person, and you're going to be the blood person.
I'll be the mild blood
be the
person.
blood
I'm still the
person.
country doctor, though.
Oh,
I'm not losing my title.
You're the country doctor, twice board certified, and today,
a true nephrologist.
You become a nephrologist.
I hope.
I wanted to show.
I should have brought a cap and gown for the end of this.
Absolutely, you're going to graduate.
Ceremony.
You're going to graduate.
That's it.
Now, I found this paper from the summer of 1997 from this professor at the University of Michigan, and I think he's a professor of I think he's a geography professor. Okay. And because he presented this paper at the American Association of
Why Whales Don't Freeze, or Kidney-Shaped Airports, Spatial Analysis and
so this
Spatial Design.
Yeah, so what he did there, I found this, I think I found this in the early 2000s, and loved it. And I loved that the
You've
professor
always
was,
loved good analogies.
Yeah, I thought
it's
that,
how you teach. It's one of your things.
And so,
for sure.
Since he was a geographer and not really somebody who thinks about the kidney a lot, I thought this would be great. And he said in the title, kidney-shaped airports. And I said, oh, yeah, man, this is it. So he came up with the analogy to airports, and I extended that in what I'm going to show you.
Cool. Okay,
but what he does first, here's a picture from his little paper that shows the whale's countercurrent exchange system. Mm-hmm. And again, he's interested in the boundaries. And so, this is why the whale doesn't freeze. And then he this is his figure of a view, 1997 view of a terminal at Chicago's O'Hare Airport. And being a native Chicagoan, I immediately agree with him that the aerial view of the terminal in Chicago's O'Hare International Airport looks like the kidney. Mm-hmm. And here are, these are the tips of the Loop of Henle right here. And this is where people are being concentrated at the terminal. So I'll go over that analogy a little bit and bring it to the whole body. But it was his idea, okay? And I loved it because he put two things in that I love, Chicago and kidney.
There you go.
And
Perfect.
And so because it started to answer the question that I've always wondered about, why are kidneys kidney-shaped? And why are airports kidney-shaped? And the answer, I think, is airports are kidney-shaped and kidneys are kidney-shaped because if you want to have a small space with high concentrations of something, like a terminal has a high concentration of people, and the tip of the papillae have a high concentration of solutes, you shape yourself like a kidney.
Right. You have to funnel things down to where you get that little transport section where everything happens.
And we're going to see that at the micro level with Confocal and great studies. But I just wonder, did the people who designed the airports, were they thinking of
they were nephrologists. You didn't know that?
Well, I don't know. But were they thinking about the kidney at all?
Mathematically, they were definitely thinking about maximizing transport.
Yes, from an engineering point.
From an engineering point,
but did they say, oh, yeah, it's going to be kidney-like, or did they actually reinvent, a building that looks like a kidney?
Yeah,
and it doesn't matter, but it's interesting to think.
It is. It's awesome.
So I'm just putting this up. I'll come back to this later, but anyway, the analogies are here, the 15 different things that are analogous, where O'Hare is the kidney and downtown Chicago is the heart. And passengers are solutes, and there's an aorta in there. And, I'll go over this later on. Cool. But I just wanted to show you that I do include the vasa-recta. They're the roads into the city. Good. Yep. So, and the Loop of Henle is all there.
Love it.
And even the interstitium, the airport hotels that keep people close by the terminal. I mean, when you're worried about missing your plane, and you don't want to sleep at the gate, where do you sleep? You take a little shuttle, a little shuttle bus.
That's it.
To the airport, and the shuttle buses, they just recirculate.
They're just recycling people.
Exactly.
That's it.
That's it. The shuttle buses are the urea transporters.
That's it.
Yeah. They're the people transporters.
I love it.
So so the hotel shuttles are the urea transporters. Yeah, so we'll get into that.
All right.
So getting back to it, the kidney, as I said, it combines countercurrent exchange with countercurrent multiplication. And so who are the players that make this happen? And special. It's very special.
Yes.
The tubes we've talked about now, the U-shaped tubes we've talked about now, had a generalized permeation for heat or something like that. But they weren't that different at any given part of the loop, okay?
Right.
The flow was in a direction.
Right.
And then there was this diffusion. But the two sides of the tube did not have different properties.
Yes, exactly.
But that is not the case in the beautiful kidney.
Exactly.
In the beautiful kidney, we have a hairpin loop with what's called axial heterogeneity. So the kidney has combined this, tubule. I'm going to build a tubule. I'm going to build it. Not only am I going to build it to go from superficial to deep, and then put a hairpin in and come back up. But I'm also going to endow the going down part with different properties than the going up part.
Yes.
And I'm going to give it some special neighbors.
Yes, exactly.
So the descending limb is going down but permeable to water. Then once you turn the tip, there's the water permeability is gone. And what you now have is a solute permeability. And some of that is passive.
Right, the thin ascending limb.
Right, and some of that is active.
Yeah.
And it's the active part that's responsible for the fact that you get countercurrent multiplication. And then the neighbors, the vasa-recta. Yeah. And then the kidney has this interstitium, which is a buffer zone.
And I think even in the vasa-recta, that there you would have the same few players, that there's a descending portion and an ascending portion, and they're different.
They're different. Yeah. And so both of them, the multiplier part is different. Yep. The countercurrent exchange vascular part is different. So the kidney, the kidney is the place where nature experiments and works out its best systems. I mean, that's the jams. I mean, when you're improvising and you're jamming, it's the kidney that does
this. Is the kidney's jam.
The kidney's jam. And so the interstitial buffer zone is that. It's this interstitium, and it also keeps things where you want them to be, like the airport hotel does. Yep. And then there's the recycling center for urea. And again, something that people need to keep in mind, especially because this is one of the favorite board questions, I think, is that ADH we think of as just inserting aquaporin 2 water channels in the collecting. Certainly that's its most important thing. But one thing that's a nuance that's important to know and key to the fact that you can concentrate your urine is that once you're in the inner medulla, the presence of ADH also promotes urea transport.
Right.
Because when water enters the interstitium deep, that's a threat to the concentration. So the urea comes right in. And it's urea, not sodium, because sodium's already, maybe its gradient is in a different place.
So ADH also regulates the urea transporters.
I believe so, my friend.
Interesting.
I do.
That's awesome.
I do, because there's no doubt that ADH stimulates urea transport, and there's no doubt that the urea is transported by the transporters.
Mm-hmm.
Yeah, and so those are the main players. And, of course, the length of the loop is very important. So the kangaroo rat, the desert rat, I think, these are animals that I'm told may go through their whole life without ever seeing a drop of water. And their urine is gravel, if it has to be. That's got to hurt.
That's got to hurt.
So how do they do it? Well, the way they do it, I mean, as you will see, humans, we can concentrate maybe to 1,200. Dogs can do more. Dog nephron is longer.
Right.
And dogs can have a higher specific gravity. I mean, the human specific gravity for the urine doesn't have to go up as high as the dog. So we can measure specific gravity, on our dipsticks or whatever. But when you're measuring, a veterinarian has to use, I think, a wine specific gravity meter because the dogs concentrate more. But the desert rat can go to 9,000. And maybe I've seen 10,000 in places, but 9,000 milliosmoles.
Wow, if we transplant pig kidneys, then they have much higher. I wonder what's going to happen to water balance.
I think the pig kidneys are pretty similar to human.
Are they?
Yeah, I think they are. I think
I might want a dog kidney.
You might. I think pig kidney is more similar to human than dog.
Okay.
Dog is our best friend.
Dog is our best friend, but pig is our best organ donor.
I think pig is our best organ donor.
All right.
So the length of the loop is key. And of course, the transit time is key. Can't ignore this. The slower the transit time, and again, let's face it, the proximal tubule has done a favor for the diluting segment and concentrating segment, because the proximal tubule has reabsorbed isotonically 2/3 of the filtrate. So we're down to only 33% of the filtrate going down into the beyond the proximal tubule anyway. And then we're going to talk a lot about the spatial and geometrical organization, the intimacy of these things, and then active transport. So it turns out that in when you have a U-shaped tube, if you want to have a, quote, multiplier effect, and again, that's a weird name, multiplier, but we can talk about that. But what you need is you wait till the end, the distal end of the tube, and leak out some stuff, because you don't want to do it too far down when the concentration gradient is too big, maybe too big. But you just do it at the end. It turns out to be efficient, and we'll talk about why. And that turns out to be the single effect.
Right.
Now I'm going to tell you where I was when I first heard about the single effect. Where were you?
I was in my fellowship.
Okay, so I first heard about the single effect, and I remember this quite clearly. I was a sophomore in college, and I was taking my engineering courses, and I was taking, at that point, engineering physics, where we were doing fluid dynamics, fluid mechanics.
Okay.
And I was taking physiology because that was part of the bioengineering program. And I loved my first physiology course. And the book we used was by Arthur J. Vander from the University of Michigan. It's a great book called Human Physiology. And I remember the picture. I don't remember the page number, but it was chapter 6, figure 13.
Okay. It
was in the upper right-hand page. And it showed the single effect that we're going to talk about. And it was all these still panels of stop motion. And I was looking at these things. I go, yeah, but this is just to demonstrate it, because these things never stop.
Right.
These fluids are always moving. And so the engineer in me, a physiologist in me, so I got to understand
it's a dynamic process.
But the engineer in me said, as soon as I understand what they're talking about, I'm getting rid of this delta osm of 200 millimoles per milliosm per kilogram of the single effect, because that can't be what's going on. The flow doesn't stop.
Right.
And it's always going.
Right.
And you only need a small gradient to keep it going. You don't need 200.
Right, yeah.
So I understand that it's a teaching vehicle.
Right.
But I think people have just learned that as their beginning and their end.
Right.
And they don't know that there's this dynamic process.
Right.
Okay. So anyway, that's maybe one of the reasons the kidney is kidney shaped. So this is where we are. What we're talking about is we're taking this kidney that looks like an airport. Airport looks like a kidney. We're taking this piece, there's a papilla, and in that piece, what do you see there, Craig? What are the key? Who are the key players?
Yeah.
in that
First
one?
of all, the outer portion there is the cortex.
Yep.
And we have cortical nephron. And then we have the juxtamedullary.
With a short loop.
With a short loop, you see there. And you can highlight it with your little mouse while we're talking. And then you have next to that on the left side of the panel, you have a juxtamedullary nephron with a deeper loop of Henle.
Long loop of Henle.
Going into the medulla. Yep.
And then
you have your collecting ducts.
Right. And you'll see.
And it's also a nice picture because it shows you how multiple nephrons connect to a single collecting duct.
Right, exactly.
Which is also nice.
I think it's important to keep that in mind because you often see just
one collecting duct.
drawing.
Exactly.
And you have to remember that
these are funneling down.
Yeah,
right.
These are because collecting duct is collecting duct.
Right.
That's why they call it the collector. So here's just a slide to demonstrate the flow effect. I'm not going to come back to this, but I did want to mention that as you have, there's going to be more of a you're going to have more ability to concentrate at slower flow rates. So here, this is raffinose, this is inulin. It doesn't matter which one you look at. But when they perfused, this happens to be a descending vasa-recta, and they just show that the permeability changes with the perfusion rate. And so when take a person who is volume depleted or something like that, their GFR may be a little bit lower, and therefore the amount of fluid entering out of the proximal tubule will be lower, and the flow will be less. And these people are the ones who have to concentrate.
Right.
And so the fact that the flow has been slowed promotes that. On the other hand, if you drink a ton of water, okay, and and that water could be at risk of washing out the medullary gradient, you want to sort of have things not have that not happen. So I'll show you that in another slide. Okay. But the flow rate matters.
Yes.
Okay. Now here's a slide for you and again, oftentimes we see figures where the nephron simplified to just the tan part.
Right, exactly. And I love this picture.
And what do you love?
What I love this because it shows the beautiful interplay of the microcirculation there, which is, you got the arcuate artery.
Okay, so the arcuate artery is here.
Yep.
And it's arcuate because it's going this way.
Right.
And what comes off of that? Yeah.
The interlobule.
Interlobular artery comes off here, right?
And then you've got the afferent arteriole coming off into the glomerulus. And then the efferent is really the important part here because it's the efferent that splits off into this vascular bundle that dives down and becomes the descending vasa-recta.
Right.
And even this one, I mean, this has become so complicated in one of the articles you sent me, which I did review. It's really opened up how complex, and you're going to show us this, which I'm really excited for. But how important the vasa-recta are.
Yeah, look at all these communications.
Right.
I mean, this is making sure there's some short circuits.
And this goes back to the pictures you showed of the fin and these other things where you're shunting to protect something.
Yes.
With the gill or the fin or the reindeer's foot, you're protecting the temperature from cooling the body down. And here you're protecting the osmolality.
The concentration.
Right.
Exactly.
I love it.
So again, the generating and maintaining driving forces is difficult for nature. It takes energy, and it doesn't want to keep doing it. It wants to do it and then maintain it. And so what temperature
it wants
is
to
like
do
that,
a single effect,
it wants
single time.
Yeah. And so it's for the temperature, it's working hard, and so you're preserving that driving force in the fins. And right here, you're preserving the driving force of concentration. Because concentration is a driving force. Yeah. And it takes special permeabilities to do that.
And I think and the other thing nice about this picture, which I've seen drawn different ways, but this one is nice because it shows you that the efferent, in terms of the flow, if you look at the descending limb is going concurrent with the descending vasa-recta.
Right.
And on the flip side, the ascending vasa-recta is going concurrent or co-current with the ascending limb.
Well, let's see if that holds up in the real pictures of the biology, the structure. So this is just a picture I like to show. This is up in the lab, a picture that just shows, this is dog kidney, and it shows, you can easily see some gloms, and these, and you can see that there's nephrons here. But if you take a look at what's going on, really, here's some of these gloms, and look at these real life loops of Henle, long and thin, and the hairpin loop and the interstitium between them. And then this is the schematic.
Ooh.
And I know you like this.
I love that picture.
And why do you love it?
I just love it because it shows that vascular bundle there in the outer portion of the medulla before it dives deep into the inner medulla.
Right.
And that is the shunting, and that is that shunting piece.
Exactly.
Yeah.
Exactly.
I love it.
So we don't want people to forget the intimate association of blood vessels. But let's face it, the kidney exists for the benefit of the body. And if the kidney wasn't an intimate association with the blood, then all the work the kidney is doing is for nothing. Because, the urine and the blood are always close to each other. And everything, and there's no part of the tubule.
That's a great picture of that dog nephron on the right. Where'd you get that?
I forget where this is from. This might be from Gene Oliver's book.
That's a
I think it's from Gene Oliver's 1968 classic. It's a gigantic book.
Yeah, where he perfused rubber into them or something?
The book, I'll bring the book one day. The book is about, take the biggest book you have.
I remember Dr. Kunin gave me a copy of one of these books.
Well, if it's gigantic, it's the Gene Oliver.
Like that.
Yeah, he also gave me some books.
He lent it to me. I had to give it back.
Oh, I think he gave it to me.
Oh, see, that's the difference between you and me.
Yeah, I think he gave it to me. But anyway, yeah, last I heard, he's like 96 years old. Doing great.
Love it.
Okay, so countercurrent systems, we'll come back to this now because both of them are operating in the kidney. So the hairpin loops provide a large surface area for antiparallel flow. The selective permeability processes allow the transfer. And this does not require energy. So countercurrent exchange does not require energy other than whatever it takes to get the fluid to flow in the first place.
Right.
Okay. And then the multiplier effect is gained if on the distal part, like we talked about, of countercurrent exchange, if you add active transport. And then there's more efficient if the flow is relatively slow. And here is the multiplier. Hairpin loops are the loops of Henle. The thin limb is permeable to water. The urine becomes more concentrated as you go down. The thin ascending limb is impermeable to water as soon as you turn the bend. And the urine is becoming less concentrated. But urea, which everybody should know in the blood is not an effective osm, but in the kidney, boy, is it important. I mean, that 1,200, half of that 1,200
is urea.
So 600 is urea, and then 300 millimoles of sodium chloride is the other 600. So urea is literally 50% of your urine concentration, solute. And then, of course, that's why it's recycled. If urea wasn't playing an important role, why would the kidney bother to recycle it? It does. It does. And then the thick ascending limb is where the active transport takes place. Now, it could be that the thick ascending limb is thick because it has to be thick to fit the mitochondria. I always thought, it's thick because, the outer medulla and inner medulla look different. And the look is different because the mitochondria density is higher in the, where you're going in the outer medulla where you're going to see the thick ascending limb. And that's thick because those, they say, if somebody asks you what part of the kidney uses the most ATP, I know that my answer is different than the answer that's mostly out there. The answer that's out there is
deep in the medulla.
No,
that's
the answer that's out there is the thick ascending limb.
Well, that makes sense to me.
Except for it makes sense to me, but I think that's in second place. I mean, I could be completely wrong about this, but to me, I think as somebody who's studied all the proximal tubule, and we've seen proximal tubule.
Oh, yeah.
Boy, those proximal tubules are stuffed with mitochondria.
Oh, yeah.
Okay. And the proximal tubule is reabsorbing 2/3 of the filtrate. That's a lot of energy.
That's a lot of work.
I would think, I don't know, gram per gram. I should look into it one day. Gram per gram.
That's a good question.
Which uses more energy, thick ascending limb or proximal tubule? They're going to be close. But that's where the ATP certainly is well placed in the kidney to be where those mitochondria are most plentiful, is the thick ascending limb and the proximal tubule. Okay. Now, countercurrent designs, we talked about the reindeer keeping in their heat. We talked about engineers, if you have a boiler, you want to keep the heat in the boiler. And so the coolant has to keep moving in a countercurrent way so that you don't, there's always a gradient. So the high energy gradient is possibly because of the hairpin shape and semi-permeable transport near the boundaries. So no heat pump is required to move the heat from the hot to the cold, like a refrigerator needs a heat pump, but not in this thing. So only energy is required is whatever is needed to pump the coolant through to get the coolant to move.
Yep.
So here it is. You've got here's the heat being produced, and again, even if you've got the reindeer or whatever is in the cold, even though this is 0 degrees out here, the system keeps the heat.
Right, because it's shunting.
Shunting. Okay. We talked about the airports, and I'll come back to that. But again, people are concentrated in the terminal. The airlines play a role. The hotels play a role. The shuttle buses play a role, and the whole thing's kidney shaped. Okay, so this is just my little thing. Again, why is the kidney shaped? I think that's why.
Yeah.
Because whether it's temperature or solute or people, you've got to have this shape. This shape is key.
It maximizes.
I think this is, I got to say, it's one of my favorite ways of thinking why the kidney's kidney shaped.
That's a good one.
Okay, so now let's get into the nitty gritty of countercurrent multiplication, where we're going to get into the mechanism.
Awesome.
And I always like to start with the history because, sometimes people start off as
it's built on this.
Yeah, it's built on this. You got to see where it came from and what the struggles were.
Right.
When you get the up to the moment, you don't
go right to the iPhone 13.
Right. I love, up to date is obviously the most useful resource that people use, but up to date because it has to be efficient and has to be up to date. It can't spend a lot of time on history.
Right.
And so all of the things in up to date is representing whatever's standing on the shoulders of giants.
Exactly.
Okay. And what's sometimes lost in up to date is you're
seeing those chapter.
You're seeing the shoulders,
right?
But you're not seeing. You're seeing the head of who's standing on the shoulders, but you're not seeing the shoulders of the shoulders of the shoulders.
That is a great.
Yeah, so
that's good.
So I always like to start at the beginning of when we kind of knew something. So again, the father of physiology is Claude Bernard, the interior milieu, the milieu intérieur. And in 1876, he actually introduced the idea of countercurrent exchange and said, there's a quote, wherever a peripheral artery flows alongside a vein, there is likely to be a heat gradient between them and a transfer of heat from the artery to the vein. This thermal short circuit, love him.
There you go.
This thermal short circuit carries some of the arterial heat back into the body before it reaches the periphery. So he was basically predicting or saying based just on, he was a structure function guy, and they didn't have confocal microscope like Claude.
He just dissected stuff.
He just looked at stuff and tried to extract function from the structure.
Love it.
Then it wasn't until the early 1940s where I think this was, it's certainly not in America. This was in Europe and probably Germany. Constructed an apparatus to illustrate the countercurrent principle operating in the kidney between the vasa-recta and the tubules, mainly essentially the loop of Henle.
Right.
Then in the early 50s, Hargitay and Kuhn, also the same Kuhn, hypothesized that a small osmotic pressure difference between the two limbs of Henle's loop could be multiplied by the countercurrent flow in the loops to generate the medullary gradient, so the gradient maker.
Gradient maker.
Yeah, and so they introduced this word multiplied possibly. And, because again,
where did that come from?
Yeah, countercurrent multiplication, we all just are so familiar with it, we don't question it.
Right.
It's like a lot of things we don't
like
question.
hyponatremia.
Yeah, and people just accept it. But the question is, multiplying is a mathematical operation, and it has a distinct definition. So I wonder if strictly mathematically speaking, what we're going to talk about is a multiplier, an amplifier, and that's why you and I talked about, let's call it the gradient maker.
Yeah,
I'm the gradient maker. It's the gradient maker.
That's it.
And so this was all going on in Europe, not much going on in the United States until the late 50s when Karl Gottschalk started to do micropuncture studies. And this was going on also, at the NIH. Mo Berg's lab had pioneered microperfusion and micropuncture. And so as people were starting to measure what was going on in different parts of the nephron by sampling, the initial results of Gottschalk fit with this kind of an idea. Okay. But it was black box completely.
Right.
Except now we had some real measurements. So in 1966, Bob Berliner was one of the people that started NIH. And then he went to Yale, where he was the dean of the School of Medicine at Yale. And I have very fond memories of Bob Berliner at Yale. After he was done being the dean, he came back into the physiology department, and down the corridor from our lab was the Yale's medical school cafeteria. And every single day, Bob Berliner and Gerhard Giebisch had lunch. And,
talking potassium.
Talking it all. And
it.
so I spent some of my time trying to figure out how I could vasa-recta.
Sit at that table.
How I could vasa-recta myself.
That's it.
Into the counter-current exchange. And ultimately, I was lucky enough to have many lunches.
That is amazing.
With them. And,
cool.
you from talking to them, you had, the whole history of the field.
Wow.
Because these guys had done the first of pretty much everything when it came to transport. And that's why Yale became the place to go for membrane transport, because Berliner was there, Giebisch was there, Bullpop was there. I mean, this was the transport haven, New Haven.
Yes,
New transport haven. New haven of transport. So, it was the mid-'60s, and it was really Berliner, because of his also ability to not only do these experiments, but to write about them in a very clear way and publish them in high-profile places, that the United States started to get an idea. And then Coco and Rector, this was, I think, done at UT Southwestern, where Selden had become the presence, running the great Don Selden. So between, the Gerhard Giebisch, Bob Berliner people at Yale and Donald Selden, Floyd Rector, Coco people at UT Southwestern, you really had these real powerhouses of transport. And in 1972, and I'll show you some of the pictures, they published the prototypical model of how they thought countercurrent exchange and countercurrent multiplication went on. That really laid the groundwork for all the other work. And from the 70s till now, we have, Tom Pallone and Thomas Pennebecker, the Anita Layton, built on the work of the giants, Berliner, Berg, Coco, Rector, and also used multiple species. I mean, it was hard to get human tissue, so it was rat, rodent, and kangaroo rat. And some people were doing the physiology and the micropuncture. Molecular biology started to come around, so we could label some of these segments, as you'll see. And then, especially the Laytons, did mathematical modeling. I mean, the two big mathematical models are of the kidney, Alan Weinstein at Cornell, a great guy, who is just a lot of fun to sit and talk with. And the Laytons, really done a lot of mathematical models for this. And that's really where we are. So great insights have been provided, but it turns out, as we found this week, the more we learned about it, instead of it becoming simpler and simple to see, oh, that's how it works, we saw the nuances and the complexities, and they remain, the intermedulla is still an enigma. Okay.
For sure. And the interstitium, and I think it's just one of those things where it makes me laugh about structure function. Everything with structure has a function.
Exactly.
And that's the bottom line.
That is. Now, this is one of our bottom line pictures. We're going to come back to this picture a couple of times, but this is a beautiful picture from Thomas Pennebecker in 2008 that appeared in the AJP. And this is a confocal reconstruction. So a confocal is a microscope that uses lasers to be able to stay in a very narrow focal plane, and you can make slices through things. And once you've made the slices, you can put them back together and reconstruct. So there's, out of many confocal slices through stained inner medulla, there's the loop of Henle interacting in what he calls the interstitial nodal spaces. And why don't you describe what you see here? Let me first outline the colors. So the white is these interstitial nodes. That's the interstitium, and you can see it's kind of squished.
Yeah.
The center of attention, of course, is the collecting duct. It's always blue in the collecting duct. The red is the ascending thin limb of Henle, and the green is the ascending vasa-recta. And what's your gestalt from seeing this?
I think one thing that's interesting is that there's multiple ascending vasa-recta there surrounding that collecting duct. And all of these, the collecting duct itself is flowing potentially in one direction down.
It is flowing down.
Right. And then you have the ascending thin limb and the ascending vasa-recta flowing in the opposite direction.
Yeah,
it's countercurrent.
So you got a couple countercurrent systems
exactly.
here. And that interstitium
is tiny.
coming to a point. It's
Right.
tiny.
It's tiny.
And why should it be tiny? It needs to be tiny because it's trying to maintain a big gradient.
Right.
And you can't have it diffuse away.
Right. And what's funny is the amount of interstitium changes as you move through these portions, which
Yes.
is so interesting.
Yes, and because there's contractile elements.
Yes.
Yeah. And you had mentioned, there's parasites.
Yeah.
There are some people that say that urine concentrating continues out into the ureter. That events out in the ureter can affect. We're not going to talk about that, but I think that's interesting.
Yeah.
So
well,
again,
concentrating ability was lost in some animals when you removed those features.
That's
so
true.
that just kind of happened.
That's true. So there could be a lot of stuff going on with nerves.
Right.
And so again, these scale bars is 30 microns. So again, this is 30 microns. You can see that the collecting duct, the diameter of the collecting duct, is about 15 or 20 microns.
But I think this is also a beautiful picture because I love these three-dimensional looks, and I love this topographical look, the CT scan cut through this way, because it gives us a view of this like we've never seen in any diagrams when people talk about countercurrent.
Yeah, this is got to be, of all the slides, there's a lot of beautiful slides, but a lot of the beautiful work was done by Dr. Pennebaker's group, and so you're going to see that's where you're going to see some beautiful pictures. But here's sort of the whole putting it together. Let's see how you get there. Okay, so again, going back to 1972, you got the Coco and Rector, and again you can see it's UT Southwestern. And Kidney International back in the 70s, Kidney International, we didn't have all the journals we have now. We didn't have the Journal of the American Society of Nephrology yet. And so Kidney International was the place, and it sounds like the place to be. Kidney International,
Exactly.
it sounds like the place to be. So the influential stuff went to Kidney International because it was published around the world, and not just in America. And so here you see the title, CounterCurrent Multiplication Without Active Transport in the Inner Medulla. This is a big thing, a simple title, and it could be overlooked. What they're trying to say here is there's a place you need the active transport, but there's a place you don't.
Mm-hmm.
And so here's how it happens. So here was the famous figure that was in a lot of textbooks. Obviously, this came out in 72, so the textbooks that were published, like my physiology textbook, was from 1974, 1975.
Right.
These are the pictures that had just come out. And so you like this and I like this because, again, it's showing you that the tubule doesn't exist in isolation. There's a vasa-recta.
Right.
And here's the table of the permeabilities of the different segments. So one of the things I want to point out here is that, there's active salt transport. It's 4 pluses in the thick ascending limb.
Right.
The thick ascending limb.
Yeah.
How much is in the thin ascending limb? None.
Right.
Okay. And then water permeability. There's a huge water permeability in the thin descending limb of Henle. And then there's urea where you need it. Where's the urea permeability the highest? Down here in the
And I
bottom.
think it's shown so beautifully in the picture.
Yeah,
The
how would you go through this picture?
Yeah, I mean, I would go through that picture where you're seeing as the thin descending limb drops, water can leave there, and that's water permeable.
Mm-hmm.
And then on the opposite side, and we talked so much about countercurrent when we showed different pictures and previously, and here you see this is where you have different permeabilities in these different tubes, unlike any other countercurrent systems we've shown before with heat exchange. This is special because the two tubes are different.
Right. And one thing I'll point out here is whenever you have a conversation of countercurrent multiplication, it always has to start here.
Yes.
You have to start with the active transport step. This is responsible for the single effect. I mean, the single effect is active transport.
Yeah.
I mean, let's face it. And it's continuous. And it's taking up the energy and what's happening here is the reason it can function as a single effect is because of the absence of water permeability here. So the same exact transport mechanism that dilutes the urine concentrates the interstitium.
Yes.
That is an efficient, natural twofer. It's one and the same. It's Clark Kent and Superman. The reason that the urine is becoming dilute is because solute is being plucked away.
Exactly.
And anybody who says water follows salt, excuse me.
Not here.
Not here, baby. It would be disaster. So water does not follow salt because there is no permeability. There's a huge driving force for water to move, but it won't because there's a brick wall, watertight. And again, that dilution process of removing solute occurs because solute's added to the interstitium.
And I think this picture also shows beautifully the difference between the outer medulla and the inner medulla. Because it's in the outer medulla that you have the thick ascending limb.
Exactly, where the active transport
inner
goes up.
medulla, doesn't.
Yeah, the inner medulla and the outer medulla are defined by where does the thin ascending limb become thick.
Yeah.
But it becomes thick because it's where it's so again the structure and function are this, you can't separate them.
Linked.
And then here's the vasa-recta again, and you see a lot of these arrows showing that there's going to be communication all the way down. And then a special thing is that there is sodium transport out of the thin ascending limb here without a pump.
Right.
And that's because urea is happening here. And so urea, there could be a gradient for, the only way passive sodium transport can occur is if there's more sodium in the tube than there is in the interstitium.
Correct.
And the reason that could be is, you say, well, how can there be? They're all both at 1200. The reason it could be is they're both at 1200, but they're differential.
Yes, there's less sodium.
So urea can go in to the tubule, and that's urea recycling, and sodium can come out to the interstitium.
Yeah, and that would be more like thinking about the different concentration gradients. The whole thing about sodium plus urea adding to the osmolality is its effect on water movement.
Yes.
Because the water concentration is low there.
Right. They both affect water movement, but their own movement can be.
Yes.
Okay. Like
that's
you were saying.
interesting.
So they can have.
So
it's so beautiful. I mean, isn't it great?
Gorgeous.
Isn't
it's
it great?
Amazing.
And I think what. So you might say, well, why don't college kids get this, or why don't med students get it? I mean, at some point, people have to decide, I suppose. And there, I've always, as an engineer type person and somebody who wants to know mechanism and then the mechanism. To me, I can never get enough.
Mm-hmm.
But apparently, that's not everybody.
Yeah. But I think one of your takeaways from this, which is really important, is that this starts in the outer medulla with the active transport of sodium.
The reason countercurrent multiplication happens is because at the distal end of the loop, the distal end of the U-tube, where energy is expended, this sodium chloride comes out here and funnels down and helps make this concentrated. And then the water that's coming out here would dilute that, but then there's urea coming out here. So urea is filling from the bottom, sodium chloride filling from the top. It's a great system.
And that is the NKCC tube.
Yes, that transporter is the furosemide sensitive.
That is the one. So for you clinically relevant people,
Right.
that's an important segment of the kidney.
If you say you're not
we
interested,
all treat it.
It's hard to say you're not interested in that if you're also somebody, if you say, well, I never give furosemide.
Right.
Well, then okay. But if you're a person that gives furosemide, it's hard to find a nephrologist that
hasn't used that.
Hasn't used it. Here are the aquaporins along the nephron. Of course, Coco and Berliner, those guys, they didn't have the benefit of knowing. They were intuiting what must be happening.
Mm-hmm.
And so what you see is aquaporin 1 here, which are the green dots. Aquaporin 1 is the water permeability that allows, it's the reason that, quote, water follows salt in the
right.
in the proximal
it's the
tubule.
Door.
It's the door, is right. And then, that continues down both the vasa-recta and the thin limb. Now, in the vasa-recta, it actually stops short of hitting the bottom. And I'll show you this. Aquaporin 1 goes away.
Mm-hmm.
And then let's see what happens here. And then, the blue, is it the blue dots that are aquaporin 2?
Yes.
Yeah. So the blue dots, of course, 88 sensitive.
And then there's some aquaporin 4 there.
Yeah. But I mean, the aquaporin 3 and 4 are basolateral, and they're constitutively open. But that doesn't matter if there's no aquaporin 2 apically.
Right, yeah.
You can, if you have two exits.
Yeah.
But if nobody's coming in.
Right, exactly.
So aquaporin 2 is the rate limiting step because it is apical.
Right.
And it's the only one that's apical.
Okay.
So yeah, but this is, again, this was published, what did that say? 2000.
That's 2020.
Yeah, so
Jan
this is
of
kind of
2020.
this is kind of up to date where we are. So these dots are not just randomly placed. When they stop the dot here, when they don't put a green dot here,
they meant it.
They meant it. And that's what I'm saying. I mean, you got to really look at some of the detail there. But
Absolutely.
I love it.
Yeah, man.
So
they spent a lot of time laboring over this drawing.
Yeah,
but boy, that's an ugly glomerulus. Look at that tubule. What, did he have his kid draw this picture? We need to go back to this Dr. Sue.
Yeah. I don't know. I mean, I agree with you but I think what they were saying is, hey man, let's line out the aquaporins.
I feel like we could have helped him with
out
this drawing.
But yeah, it might have been helped. I mean, and the journal didn't redraw it. So
oh my God, it looks angry, that
Looks like a snake,
It
right?
looks angry.
Yeah, it looks angry. But I agree with you. But we appreciate the work.
We do appreciate it, and we
appreciate
like
the
the
work.
Aquaporin placements.
Now let's go back to 1972.
All right. Now that's a nephron. Now
There's
look
a
at the drawing here. It's like,
1972.
at least it's like,
This was hand drawn.
I know. Come on. These guys knew what they were doing.
I know. So here, what you're seeing, again, what you don't often see because it's deleted for simplicity, you often see this, the long loop.
Yeah.
But again, there's the other nephrons
Right.
with the short loop. And of course, look what happens. The outer medulla is where the short loops stop. The short loops don't get into the inner medulla, and the long loops do. And look how this is labeled. 1972, they already knew a lot of things. Water's coming out down the descending limb.
But they do play a role in the single effect. So
Yes.
they amplify
Yes,
the
because
single
they're-
effect, but you don't need that many.
Right. They
Yes.
amplify the single effect because they're in the right place to do it.
Exactly.
And they have the transporter. But you notice here, as you the water permeability coming out the descending limb, and then sodium is passively moving out. The only way sodium could passively move out again is if the sodium concentration inside here is higher than it is in the interstitium. And urea is one of the things helping that. And you see that urea is moving in and sodium is moving out. So the urea and the sodium gradient are oppose each other. That's kind of cool.
Mm-hmm.
And then, again here, and then you show the whole system. This exists. I mean, there'd be no point of having the loops of Henle if there wasn't a collecting duct where the final decision is going to be made by ADH.
Right. Yeah.
This collecting duct is either completely impermeable to water when there's no ADH or really permeable to water when there's ADH. So this was I remember that not seeing this part of this figure. Seeing this figure many times, but without that part of it.
Right.
Somebody whited it
that's
out.
a good point.
Not so good.
Yeah.
So, okay. So then Coco, a few years later, Coco and Tischer, again, still from Coco at Southwestern and Tischer from Duke, looked at the water movement across nephron segments. And again, and the model still looks pretty much the same. And this is the one, again, now you're only seeing the one nephron.
Right.
Okay.
Yes.
And
right.
this is the one that everybody, this is the one that everybody, I don't know, maybe this one got translated to Brenner and Rector's kidney book.
Oh,
because
right.
it was Rector was on both papers, but maybe it was time to just say, okay, where are we going to be with this? But this is the classic.
How you learn it.
I mean, this is the classic. I think a lot of people have seen, and if you haven't seen it, look in one of your books. It's there.
Right.
And again, here's the single effect or the active transport that has to do with the starting point and all the important players. And these arrows are different than I complain about the multi-arrow diagrams. These arrows all have a purpose. So these arrows, especially if they're curved, these guys were careful.
Mm-hmm.
And so again, the debt that we owe these scientists that worked
It's
hard,
on their
you
shoulders.
got to remember there was no internet.
Yeah.
There
That's
was
right.
no word processors.
No.
Everything was typed. Everything was drawn. If you copied and pasted or cut and paste, you used a scissors and a glue stick.
Yeah, exactly. Hey.
So this was tour de force work, and we didn't have confocal microscopy.
That's true.
So now what happens when you do? So here's the mathematical modeling. This is a paper. I should have put the reference on there. So it's from the Laytons.
Oh, we can put the reference down. I'll add the reference in.
Yeah. So this is from the Laytons, and I can well, it doesn't matter. But this is now giving you that freedom. You love this because you're seeing the transverse and the longitudinal, and you're seeing that this is a complex. I mean, I'm not going to belabor the detail of this slide. It's beautiful, but I'm only showing that they went to the trouble of showing the outer stripe and the inner stripe to show that the center of attention is always the collecting ducts, but the environment. I mean, look at the different ways that these things are arranged. Look at these vascular bundles.
Right.
These intimate relationships structurally. So they're intimately localized next to each other in a lateral sense, and then to go along with this vertical gradient maker.
Right.
And it's all subserving the same function. So it's just beautiful.
And then you can appreciate in that picture these planes almost like that. As you look through those, you can imagine this is the axial gradient. It is this sideways stuff happening here.
Yeah.
Along with flows between the sideways stuff that's making things amplify. And I love it.
Well, I think that you're it's looking more and more likely that after this session you'll be a physiologist.
I don't know. It could happen.
Could happen, or we're still not sure.
We're not positive. We're not at the end yet, but we're working on it.
So here's what's all happening. Here's the reason we're doing all this. So this is the classic drawing, and I love this: the tubular fluid over plasma ratio. This is the real deal.
Well, this is good. I didn't see this one.
So this one shows that here you are. You start off in the glom proximal tubule from Bowman's capsule to the proximal tubule. Look at this flat line. What does a flat line mean? Does it mean that nothing's happening?
No, it means you're isotonic to plasma.
Yeah, it means that because of aquaporin 1, all the sodium transport, because of aquaporin 1, is isoosmotic, isotonic. Right. So that along the proximal tubule, there's no change in the concentration. And so whatever, if it's 290 here, it's 290 going into the loop of Henle. Now here's the loop of Henle. Big change here. Big change. Now what's the difference between the red line and the blue line?
Go ahead.
The blue line is when you have a high flow. This isn't washout. Okay. This is high flow.
Yeah.
So it may not be this big, but this is not my drawing. But this is the action. And this is where the students
They should have changed the colors. They should have split the green into like two so that you had the descending limb, the bend, and then the
I agree with
limb.
you.
Because that is so important there.
Right. But you see,
it is cool.
You see, you say that now with the benefit of having looked at this and thought about it, whereas from the point of view of, well, this is going to go in a textbook,
right?
And they want to not have too many colors.
No, I get it.
Maybe have to pay extra money.
No, that's true.
But this is the part where students say, wait a second. First of all, nothing happened here.
Right.
So I mean, if you're not paying attention, you might say, okay, so here the first part, kidney does nothing.
Right. Why don't we just get rid of that segment?
I don't know if we need that. Nothing's happening. And then I appreciate something's happening there, but then you undid it.
Take it away.
So let me get this straight.
Hold on.
Am I going to go into nephrology? Am I going to go into a field where the first part of the proximal tubule is nothing?
Right.
And then the loop of Henle does something and immediately undoes it.
This is like the bank account. You save your money, then all the bills show up, and then boom, you're back to zero.
Exactly. So the reason is that none of this looks like anything until you see what's coming at the end.
Right.
At the end, what's coming here is if there is no ADH, then once you're past this point, there's going to be no water permeability out of the tube, and you're going to excrete a urine that is, not very concentrated. Right. It's going to be a dilute urine. You're going to excrete all your water. And here's what's happening into all these different parts of the tubule. The distal tubule, there's more dilution because there's sodium transport through the thiazide-sensitive co-transporter. And then there's a reabsorption of sodium through ENaC. And so the urine can be quite dilute because all the solutes being taken away and the water is staying. And then here's the difference. The difference is everything looks pretty similar, but if ADH is present in the ADH sensitive segment of the nephron, aquaporin 2 gets inserted and boom.
Yeah.
Make a concentrated urine. So
and all of that happens because of that steep peak in the second section at the loop.
Exactly. So this could never happen. It's not coincidence.
Right.
This
that
comes
those
back
two
to
match up.
Yeah, they match up because this is what you made for this segment. So the loop of Henle exists for the benefit of the collecting duct. The collecting duct's the boss.
Yeah.
Okay. And these are the workers. These are the worker bees.
But it looks like that's only getting to about then what, 900 because they have a ratio of 3 there?
Yeah, this one I think this is well, I mean, we always say 1200.
Yeah.
But I think we did a this, I'm not sure this is legal anymore, but in our lab, I don't know if you were in the lab when we did this, but we had, young, healthy nephrology fellows like you. Mm-hmm. Rob Whitehouse was there at the time.
Okay, yeah.
And where was Rob compared to you?
He was a couple years behind me.
Right. So definitely when Rob was in the lab, I think we did a test to try to see. They noticed I drank a lot of coffee and Diet Coke with caffeine in it, and they thought that's why I peed. I go, no, it's because of the water.
Right.
And so we did this study where I drank all my caffeinated stuff, and they drank a lot of water. And we compared urine outputs, and since we had the osmometer,
right, measured osmolality.
And so it turned out, of course, I was older than Rob, and so I couldn't dilute as well as Rob.
Right.
But Rob, who at the time was probably 28,
yeah,
could dilute not even to his age. So he could dilute to, I think he could only dilute to basically 50.
50.
Maybe a little lower.
That's pretty good.
And but we never tried to thirst ourselves to see what we could concentrate. But the reason I'm answering that is because, the usual extremes of young humans can dilute to 20.
Right.
The kidney cannot excrete distilled water. 20,
Right.
20 is it. 20 to 1200. But in real life, by the time you're an adult,
yeah,
most adults can't get to 20.
Right.
And you never in the hospital see anybody get close to 1200.
Right.
And out of the hospital, I don't know how close people can get, but 1200 is the top. I mean,
yeah.
Sometimes I've seen books say 1400, but humans,
yeah, not so much.
You don't see. I've seen people with severe SIADH. They're not getting much over 1,000.
Yeah. 900.
Yeah, it's that's enough to give you bad SIADH.
Right.
But they're not going to 1400.
Right.
So I don't really know. But one thing I do know is the lowest urine osm I've ever seen in my life was a 35-year-old who collapsed on Church Street in Burlington there, who was he was found down in a pool of urine. And he was a psychogenic polydipsic.
Wow.
And he was 35. And when he came into the hospital, urine pouring out of the Foley. We had to give him DDAVP to slow him down.
Wow.
Because the sodium was 112. And, I remember pictures and I remember numbers and I remember every joke I've ever heard. But I can remember this guy was pouring out the urine and we had to give him the DDAVP to slow it down because he was going to correct too fast.
Right.
Okay. Who knows how long he was hypotonic. And
probably a while.
And before with the DDAVP, we sent this urine, and it was the lowest urine osm I'd ever seen. It was 24.
Wow, that's impressive.
So a 35-year-old was doing 24, but he was solute depleted,
right?
And he was a psychogenic polydipsic. Yep. But it shows that's how low you can get.
Yeah,
and that's what he did. He was normal sized guy, but he was not eating much. He was just drinking all his calories. So anyway, that's that. Now to try to give you these have been all still pictures.
Yeah.
Now, two things I want to say about this. The University of British Columbia, in all my time of looking at this stuff, I remember about 2005 or so, I found what I thought was the best thing to show the students, to give them the overall gestalt of what was going on with this whole process. And it's simplified.
Yeah.
But if it's starting from nothing, this is a big step in the right direction.
All right.
Now, a couple of things to say about this. One is it was a shockwave file.
Okay.
And so it's no longer, you can't find it on the internet anymore because shockwave files are no longer supported by Adobe. But
it's about to be an MP4.
It could be something. But the good news is I have a program on the Mac here that can play it. And I thought it was, this was the best. And even though it's from 2005, I haven't seen anything better.
Right.
I remember looking for an animation and never saw anything better than this. And I just want to give full credit to these folks at the University of British Columbia, the beautiful British Columbia. Boy, what a beautiful place.
And the animation by Shelter Lee.
Yeah, what a beautiful place. But let's go. Let me come off the slideshow here and see if I can open up my other file here, which is this. Yeah. So this is a shockwave file.
Okay.
And again, it's not mine.
Right.
It says Segal CounterCurrent because that's the name of the file. But this is the University of British Columbia. And let me just show you what they did here. So there's already some nice animation rolling in, talking about and again, 3 parts. The medullary gradient, how does it get started? Okay, when you're born or whatever. And then, how do you make a concentrated and dilute urine, and the role of the vasa-recta, and also there's urea recycling in here. So it's got pretty much got all the stuff.
All the pieces.
So let's have a look at it here. So roll out of the way here. And here they are. Formation of a concentration dilute urine. Here's the 3 things we're going to do. And, there's our nephron. And so let's just go with formation of medullary gradient. So the process, they already show you that now you're just dealing with the loop of Henle. And they got the descending limb right there. They show you nice animation, the thick ascending limb. Okay, and then they've got the interstitium. There's our U-shaped thing with the interstitium. Okay, now here they bring in the features. A key feature of the first thing they say, because they know that the single effect is the active transport. A key feature of the thick ascending limb is it's impermeable to water, but it can pump sodium resorb sodium passively and actively. And then they're going to say, for simplicity, now here's what I like that. I like that they said, for simplicity, let's assume.
Yes.
Already you've left the real world.
Right.
Okay? So this, again, is just for simplicity and to illustrate points. But they thickened up the walls here to show water impermeability.
Right.
Okay. So now an ultrafiltrated plasma, which is 300, is coming in from the proximal tube. So they filled the whole tube with 300.
It's all 300.
All 300, and you see the purple shade and the blue shade. It's nice.
Yeah.
Okay? That's not how any of your nephrons are right now. It's how they started one day. Okay. And now they say, this is the osmolality of the different compartments. And again, when tubular flow is stopped momentarily, which does not happen in real life, that's when they're going to do the active transport. But in real life, the active transport's going on with the flow.
Just happening.
Yeah. So what happens first is the first effect, the single effect, the active transport, the transport of sodium, passively here, actively here. They don't line out the medulla, and what they do is they keep pumping until there's this
arbitrary gradient.
Yes, but people have taken it literally.
Yes.
And
that's true.
It's not literal. It's
right.
just this is for demonstration purposes.
Mm-hmm.
It's made up number. They could have done 100.
Right.
They could have done 50. They could have done 2. Okay, but this is what they did. They did 200. Okay, now you got water permeability, Aquaporin 1. So as soon as this becomes 400,
then you have a driving force for water to leave the descending.
Yeah,
thin
and now
line.
it's going to turn to 400. So what's making this happen is that this is also water permeability. So these are always in equilibrium in the steady state.
Right.
And the only reason this can stay 200 because you got active pumping.
That's it.
That's the active transport. So now what happens? This is referred to as the single. And again,
you just saw the single effect.
And I still don't know why
you
it's
made
called
a gradient.
It's a gradient maker.
But this is the axial gradient. This is the gradient across the lateral, across.
Yes,
right.
But the single effect, to me, it's active transport and combined with the flows countercurrent become a gradient maker.
Yes. And
because urea recycling is in there too. So I'm not sure. I still don't know, even though this was the earliest thing I saw in 1976.
Yeah.
I didn't understand it in 1976. And I still don't think it's the greatest phrase.
I'm starting to think of it.
How about you? Yeah.
I'm coming to some things as the more we've talked about stuff.
So if you're
I think it's
future,
exactly what you said. But if someone said what is countercurrent multiplication, my first part would be just what you said, which was it starts with this first active transport section.
Yeah.
That's called single effect, but that doesn't make the gradient to 1200.
No, it's a requirement.
Because if you got rid of the vasa-recta and got rid of these other portions, it wouldn't happen.
Right. But this, to me, I just think of it as it's the first thing here that allows the multiplication is the active transport.
That's it.
And so if the single effect was happening in a different place, it's happening in only one place.
Right.
Anyway.
Nice.
Now what they do is they say, okay, but they're good about this. Remember, this is just principle.
An animation.
It's a cartoon. Okay. Now what they do is they say, fine, now we've done this once. Now let's move.
Fresh water.
So they bring in fresh isotonic.
That's what I mean. Fresh fluid.
Fresh plasma.
Fresh plasma.
Ultrafiltrate.
Yep.
And then they stop it again. And when they stop it again, they allow you to do the same business again, So now extra water has come in, so now that's going to dilute the interstitium a little bit from what it used to be. But don't worry because we still got the pumping going on. So now this happens, and now the interstitium goes back up. So this is the yin and yang of the salt and the water. And this goes on for a while, and again, now it becomes just click through it, and it just basically you got this stuff going on, and the thin limbs doing its.
And I think this is the point.
It's
the new fluid, it's the new ultrafiltrate coming in, and this process repeating itself. That's the multiplication.
Well,
because
I don't know.
I don't know. This is multiplying now.
Well, what do you mean by multiplying?
Multiplying. Well, this is creating. When you first did it in stop motion once.
Yeah, 6 times 7 is 42 is multiplying.
No, that is multiplying.
Yeah.
But this is amplifying the gradient.
Oh, amplifying. Okay.
Amplifying.
Maybe just making it.
It is making it.
Gradient maker. Okay, so anyway, this continues and goes on. And again, the thin limb is doing its water thing, and the thick limb is doing its salt pumping thing.
Right.
And because of all that, and then there's the interstitium is doing its buffering thing. Mm-hmm. So there's 3 players here. There's the descending limb with its water thing, and the thick ascending limb with its salt thing, and then the buffer in the interstitium.
And
so
I
what you're
think
seeing
one
here-
other thing that they're
Yeah.
missing, of course, I always got to bring up the vasa-recta because
they're going to bring it in later.
right, which is good, but that's bringing away some of this extra water because as this water is being pumped out into the interstitium, it's dropping.
It is. It is.
And
If
that
there
doesn't
were,
help
if there
you.
weren't vasa-recta to shuttle this water away,
Right.
there'd be some trouble. So this goes on for a while, and then I think in the end, and I think I can maybe skip to the end of it here, you get this, you get something. And I'll just move it along here because I think
That's
for
okay.
some reason it gets stuck. Life ain't perfect. So that just shows you that. Now let's move to the next step here, where here what we're going to do is they're going to show you the formation. And again, it's going to just, now all of a sudden collecting ducts here.
I love it.
So now they add in, they showed you the Loop of Henle,
Mhm.
and now they're showing you the collecting duct. The proximal tubule fluid is isotonic. The descending limb is identifying all the things, which is very nice. And then there's the thick ascending limb. And then, of course, there's your distal tubule and your collecting duct. So they're very good about lining that out.
Yeah.
Very simple. And now they say, assume the medullary gradient's already there. So now it's going to turn,
Okay.
oh, look at that. Now, all of a sudden, the steps are going a little.
Gradient maker is there.
It's gradient maker. There's for simplicity, let's assume it could, but it's continuous change. Okay. So now what happens? They separate it, and now they've got your numbers here, and they got 1300 whatever. And now it's going to be the water diuresis. So the water diuresis is that the 300 comes in, and it's doing its thing. Initially there's no transport of water because everything's 300, but then there starts to be water transport out, and as this continues down, you see more and more water transport out. That reinforces the concept of how the thin limb is working. Then all of a sudden, you're 1300 at that tip, but now what's happening is sodium can leave. And this is passive leaving of sodium. So they're correct.
Right.
This is passive leaving of sodium. It's keeping the interstitium concentrated. And now you're coming into the active leaving of sodium. So even though they use the same icons, this is pumped. This is like because you have a sodium potassium ATPase, and this is passive. Okay. And again, as the urine is being diluted, the interstitium is being concentrated. And now what happens is at this point, you don't have antidiuretic hormone. So once you made the 150, you're letting it all go because there's a huge driving force for water, but no permeability for water. And that's how you make a large volume of dilute urine. And then again, to go the other way, you see here, some of the reabsorbed urea in the interstitial space can enter the loop of Henle, either descending or the ascending, and this urea is trapped. Again, keeping low here because the sodium gradient is still outward from the tubule, but the urea gradient is inward. Okay, and then so urea just sort of recycles around, and they show it in a way, I don't know how there's urea transporters doing this.
Yeah.
Okay, and now put it all together. And so what they say there, they said this process of urea leaving the interstitium is called urea recycling. Okay, fine. Now putting it all together, there we have it. What you got is water not doing anything net when it's 300, then water going out and this becoming more concentrated, then sodium going out, but water not going out.
Right.
As you get this passive transport, active transport, and then now ADH puts in the water channels, and so this water is being reabsorbed because there's ADH, and you excrete a small concentration, a small volume of concentrated urine. So this is the kind of the end of it. Except where they
that is a great diagram.
Yeah, it's great. And so the one they do one more thing. They do consider the vasa-recta somewhere here. So let's just see. So now the vasa-recta is the capillary network, also a hairpin loop. And now they're putting in the vasa-recta for you. It's not going to be as complete as you want it to be.
But
it basically is going to show you that the vasa-recta function in this kind of way that there's a countercurrent, and that it's also at the same level. So the vasa-recta are water and solute permeable, different places, and we're going to go into detail on that next. But this is why I always thought this was the best animation out there. So now let's go back. That's the end of this. Let's go back.
There, what's interesting is they show sodium and water both moving, and that's probably not what's happening.
It's probably not.
Yeah.
Let's see what is happening. So going back to our PowerPoint, to our slides, I think
great video, Alan. I think really
again, it's not mine. It's the University of British Columbia.
Yeah.
But again,
a great learning tool.
I thought that in the time since this was made, and even after the time that shockwave is no longer provided, that there would be something somewhere else on the web
available.
There's no good animations.
No, it's true.
So we're going to do it ourselves. So here is a favorite article of yours. I think you said to me when you read this. This is again a 2003 review by Tom Pallone and Rex Jameson, where when you read this, just the beginning of this paper, you can tell it's the beginning because this is
I'll read
small
that.
caps. This is really, I agreed with you when you said, boy, this is really the best description. I think it's worth reading.
Agreed.
Go ahead.
So since the experimental findings of Words et al. Led to the countercurrent theory of urinary concentrating mechanisms as described by Hargitay and Kuhn, most subsequent research has focused on the countercurrent multiplier function of the loops of Henle. According to the theory, a small difference in the osmotic pressure, the Segal effect, is multiplied by the countercurrent flow in adjacent channels of the limbs of Henle's loop to produce a large axial difference in osmotic pressure between the renal cortex and the tip of the renal papilla.
See, so right there, they're saying that the single effect is a single effect.
Right.
And then the multiplication is because of the countercurrent.
Right.
Okay.
Yeah, that's amazing.
That's fine.
Yeah, I think that is the multiplier generates a hypertonic renal medulla.
Gradient maker.
It's a gradient maker. Right.
Okay.
Less attention has been paid to countercurrent exchange, which is thought to preserve medullary hypertonicity rather than create it. Interesting.
Yep.
Yeah, it's generally accepted that the microcirculation of the renal medulla functions as a countercurrent exchanger that traps sodium chloride and urea deposited to the interstitium by the loops of Henle and collecting ducts respectively.
Right. So this gets into the vasa-recta, which is what you like.
Right. No, exactly. Early hypothetical descriptions of this process envisioned a system in which descending vasa-recta and ascending vasa-recta are parallel tubes that equilibrate by diffusion. According to that notion, blood flowing from the corticomedullary junction toward the papillary tip and DVR is concentrated by the diffusive influx of sodium chloride and urea, and conversely, by flowing away from the papillary tip toward the corticomedullary junction of the AVR, is diluted by diffusive efflux. That theory predicts that solute is trapped by due to recycling between DVR and AVR, and that net rate at which solute is removed from the medullary is primarily dependent on the AVR-DVR concentration difference at the corticomedullary junction.
Right. So they couch it in terms of saying we're not really sure.
Right.
You know, so this is what people have said, and maybe. So here's a favorite diagram.
Oh, this is a great diagram.
Okay, and I can't hardly see it, so why don't you go ahead?
So when I look at this diagram, there's a couple of things with it. First, it nicely breaks out cortex, outer medulla, which it breaks down into the outer stripe and the inner stripe, and then the inner medulla. And in terms of the vasa-recta, you know, I go back to, you know, the big thing is that the efferent is really what turns into the descending vasa-recta. So the efferent arteriole comes off the glomerulus, then drops into the outer stripe, and then it turns into this vascular bundle, which you see there in the inner stripe.
It almost looks like the difference between the outer stripe and the inner stripe is before you get the
bundle.
Plexus.
Exactly.
Yeah, so the plexus of more vascularity.
And this reminds me of all those pictures you showed us of other things shunting, and this is going to be an important part of protecting your deep intermedullary hypertonicity by shunting water away before it can go down there and dilute it.
Exactly.
And then you have the descending vasa-recta, which goes deep into the inner medulla, and then ascending vasa-recta. I think one other thing that was important, which is in the text of this, was that the efferent splits off, I think, into like maybe 30 descending vasa-recta.
Right.
So it really...
we're going to see that diagram.
Yeah.
But yeah, this is a great picture.
It's a great
picture.
picture.
Shows you what, I mean, you know, anatomists named these, you know, cortex looked a certain way, a certain level of tan. And then, you know, that's where the gloms were. The gloms either had to be, you know, up here in the cortex or at least no further than here in terms of the junction.
Right.
And then there was going to be the medulla was wherever the gloms weren't. and then they would divide it into outer and inner medulla, outer and inner based on the thickness of the thickest, and then would change the color of the tissue.
Mm-hmm.
And then maybe these blood vessels change the color of the tissue. I think the
Right.
stripes are, I mean, when you think
It's
of
so
stripes, it's
interesting.
colors.
Yeah,
you know?
right. No, exactly.
So, I mean, I don't really know.
Yeah.
But, I mean, my simple way of looking at it is that the cortex is where the glands are. That's the rule.
Yeah.
Wherever the glands aren't, it's the medulla. The outer medulla is where you got active transport, a lot of mitochondria.
Yep.
And the inner stripe and outer stripe are distinguished by the fact that there may be more blood vessels in the inner stripe.
Yep.
And then you got your inner medulla. So the inner medulla doesn't have two stripes.
One other thing that I think they brought up in this picture, which I think is nice, is that as the efferent drops, these are arterioles, and we always talk about them as resistance vessels.
Yeah.
But those smooth muscle cells disappear as you get deeper and deeper into the deep medulla.
Right.
And you have this little remnant, which is that parasite.
Yeah. And the parasites have, again, I think what happens is that things that have been ignored for a long time become, so somebody's trying to figure out how to get a grant.
Yeah.
And I said, what have people ignored? So for 100 years, everybody ignored the primary cilium and the principal cell. And then Ken Spring at the NIH is a great guy. Ken Spring decided, maybe look at this thing. And all of a sudden, there's the flow sensor.
Right.
And all of a sudden, PKD world is shaken.
Right.
Because then everybody goes, how could we miss this? 100 years, we ignored this.
Right.
It's
amazing.
And then, for a lot of years, parasites were ignored. And the reason they were ignored is they're tiny.
Right.
They're difficult to work with.
Right.
But then people like Tom Pallone and these other folks have figured out they play a very important role. So a lot of times you don't know if something's been ignored because it's ignored because it's not significant, like an appendix.
Mm-hmm.
When they first took, we're going to take out your appendix.
Or it's difficult to study, and these cells
Yeah.
are difficult to study.
Yeah, they're difficult to study. So things get hot based on, channels got a lot hotter when we could patch clamp them.
For sure.
All right, so here's some of the beautiful, and this is just in time for Christmas. Right now, this is the last couple of days of this 2021.
Yes.
So, since I can't see, I labeled the things here. These are transverse sections through the inner medulla from the same paper. So what are you seeing here, Craig?
Yeah.
The red is the
Aquaporin 1 for the descending
Loop of Henle.
Yep. And then green is the urea transporter for
Yep.
the descending vasa-recta.
Yeah.
And then you see them clustered around the voids, which are the collecting duct.
So what do you make of the red and the green's relationship to each other? So the red, remember, red is carrying urine.
Yeah.
Okay, it's a little bit confusing because you think red would be blood.
Right.
But
Exactly.
But the green is the blood.
Right.
And the red is the tubule. So
Yeah.
what do you?
I mean,
get?
those
what
are both
do you get?
descending. Those are the descending loop and the descending vasa-recta.
Yeah, and
So
they're
going-
pretty close to each other.
They are close to each other.
And are they about the same number of them? Are there more greens? Or to me, I mean, looking from far away, the greens and the reds look
They're
like
pretty similar.
Pretty similar.
They're pretty similar.
Beautiful.
They are.
And then here's at the bottom of the same slice. What you're seeing here is the urea transport for the thick ascending limb. So the thick ascending, if you would, they were both green, so they didn't put them on top of each other. But if you superimpose this, here's the thick ascending limbs that would almost seem to be right in there, because they're
Yeah.
all over the place.
Right.
And they're kind of uniform. Or here I kind of get like a double helix almost. The
Yeah.
green,
They look like
the green is helically related to the red, and they're kind of really intimately involved with each other and
Right.
hugging. And then all of a sudden you got the thick ascending limbs kind of uniformly, and the collecting ducts and the thick ascending limbs are close connected. Okay, so what do you see here?
Oh, this is beautiful.
Beautiful, isn't it?
This is that 3-dimensional reconstruction.
Okay, so what do you
And
think?
it shows the spatial relationship. It looks like, again, we have red label.
Well, why don't we start with the collecting duct in blue because it's the star.
that? Yes, that is. And if you look in panel D, it actually looks the nicest because you see that little section right through it in D.
Right. Yeah.
So
it's at center stage. It's the
it's
star.
center
Who are the
stage, and it
supporting
drops
players?
the lowest.
Yeah.
Yep. And then you have the descending vasa-recta and the descending loop of Henle.
But which one seems to be more intimately associated?
Yeah, definitely there.
Yeah.
It looks like, it's the descending vasa-recta.
Well, to me, they're both the kittens trying to get to the mom.
The descending loop doesn't look like it's stained all the way down to the bottom when you look at the big picture in E, does it?
No, it doesn't.
Right.
It doesn't. Well, let's see. We go higher magnification. Let's
Yeah.
go higher mag.
Let's go higher mag.
Okay. So here, now all of a sudden,
Now you've added the ascending vasa-recta.
right?
Yep, and the ascending thick limb.
And so they definitely go all the way down.
Oh, yeah.
The ascending vasa-recta is going down to the bottom. And so these are, this is just showing you these bundles, intimate association. Now, here's the transverse section. So here's the answer to the question. So in the transverse section here, the blue is the collecting ducts. And you see they're the star of the show.
Yep.
And these red and greens
Are the ascending thick limb and the ascending vasa-recta.
and they're just all
Packed
supporting each
around
other,
each
packed
other.
around it. And then here are the descending, sort of on the periphery is
Right.
kind of the distal thin limb of Henle and the descending vasa-recta.
And I think that this picture is really nice on the left panel, the A panel, because the A panel really shows you that the collecting duct is flowing countercurrent to the blood vessel.
Yes,
to
these are ascending.
Vasa-recta.
Yeah, these are ascending, going back
Yeah.
up to the cortex,
Yeah.
and this is coming down.
Right.
Yeah, exactly. So it's beautiful. So here again, just more relations. Here's a higher magnification. You go up here. Here's you can see this. You're just going up more and more magnification. The red is the thin descending loops of Henle, and the green is the thick ascending loop of Henle.
Yeah.
It just shows you how these beautiful hairpins.
Yeah.
And obviously,
And you're seeing that
yeah, and you're also
capillary
seeing, you're also seeing that
design.
Aquaporin 1 is, this may be a hint of how far Aquaporin 1 goes down.
Right, and they use the separate stain, I think, as to show the whole descending limb, because it kind of staggers off the Aquaporin 1
Yeah.
as they get to the bottom, which is interesting that it kind of loses its water permeability as you get down to the bottom, at least via Aquaporin 1.
But it makes sense. It makes sense because you could argue, at least the mathematicians argue, that wouldn't be what you would want. Because at some point you want to shut off the water permeability.
Yes, right. That's it. So you stop concentrating.
Yeah, that's going to be the end anyway.
Right.
But you're at the end.
Right.
And then this picture I love. This is a longitudinal section through, I think, a rat in her medulla. And this is just, this looks like a house decorated
That's just
for
Christmas.
It looks
Got
beautiful.
Christmas all over it.
And again, starting at the blue, being the collecting ducts, you see blue throughout the whole thing. The Aquaporin 1 of the descending limbs, you see that goes almost, to the tip. And then the urea transporters of the descending vasa-recta. It's just beautiful. But it shows you that this isn't just accidental.
No, and I think these pictures are always nice because they just take us away from that nephron diagram.
It does, right?
And they show us
What it really looks like.
what it really looks like.
Right,
And it's really awesome.
I think you get a whole different kind of
perspective.
Right, you do, and it's easier to understand that this is all continuous and not discrete. So this is a recent review. I think this is the most recent review I could find. It was beautiful because it's Pannebecker again.
And they always talk about it one nephron doing this. But it's nephrons communicating with each other.
Yeah, that's right.
In relationship to
And
each other.
why wouldn't it be?
And why
It's a
wouldn't
network.
it be? It's a network. And I think that's the other piece.
Right. So this is a very nice paper that came out in the Journal of Comparative Physiology, which shows that they're going to talk about different. When they say mammalian, I think that's because they have rodent, and they have other species, fish maybe. Where and this is not so long ago, 2018. 2018. They go through the detail of the transporters. But what I want to show you here is just, here is really what they're showing is our current understanding. So you can read these better than me.
Yeah,
so
that's
what this is showing,
positive.
yeah, what this is showing is you see you see that it stops short of the tip.
Yes.
I think that's what what I'm getting out of this.
No, that's for sure.
So,
yes.
yeah.
Yep, and it shows in the descending thin loop that it's aquaporin positive, but about 15% before the end. I think they said millimeters before the end. They measured it actually.
Yeah.
It stopped aquaporin.
It also shows 4 different kinds of nephrons here. The cortical nephron that stops, and then different lengths. That there are nephron. There's a heterogeneity of length of the long ones. So the long ones aren't all as long
And,
as
and what was funny is, if you look, and I didn't know this, I'm just seeing this really for the second-ish time,
Yeah.
that it's aquaporin 1 negative on the descending thin limb
right.
of that cortical.
Right. So they stop. There's a point at which you have no more aquaporin 1.
And there's some nephrons that have none
Right.
in that first one,
Right.
which doesn't go into the outer zone of the inner medulla.
Right. So, but if you look at the longest loop,
Mm-hmm.
the longest loop has a longer negative,
Section.
we always said the aquaporins went away after the bend
Right.
or at the bend.
Right.
But here, at least of the 2018 in comparative species,
Yep.
the aquaporin, it stops short of the end of the tip.
And all those
Significantly.
diagrams that show water leaving all the way down,
Right, even
that's
mine,
not happening.
even my diagram,
Right.
which is wrong.
No.
But that's right. So again, this is where the details become important. You start
Yes,
to
it
think
is.
this is a detail and a nuance, but it makes you think. I mean, it's not accidental. Nature didn't make a mistake.
Yep.
The question is, mathematically, and I think Anita Layton is trying to answer this mathematically, why this should be the case.
Yeah.
Because nature didn't make a mistake. What we do know about the overall gestalt of the countercurrent system in the kidney is it's all doing what you want it to do.
Yes.
If the goal was, you say, here's what I want, make it happen.
Right.
So somebody, this is what you want. The kidney always has a way, and I always told people the shortcut to getting answers right on a test is, what would you want the kidney to do?
Yeah.
If you can imagine what you'd want the kidney to do,
It's
there's a
probably
good
the right
chance
thing.
that's the answer.
Right.
And
then
so,
they show beautifully the vasa-recta.
yeah,
there.
this 1 to 2.5 plexus.
Yeah,
makeup.
of descending vasa-recta compared to
Right.
ascending vasa-recta.
So I think the 2 points of this slide was to show, or maybe 3 points, is there's a heterogeneity on the length of loop. Aquaporin 1 does not last all the way down,
Right.
at least some places, and that there's a plexus formation where you get more this ratio that you just mentioned.
And I think that one of the other pieces that comes off in the descending vasa-recta is that everybody talks about salt and sodium chloride and water moving equally.
Yeah.
And it doesn't.
It doesn't.
It doesn't. It has aquaporins in the descending vasa-recta, and it mostly moves water.
Right.
And that's how the vasa-recta
And
concentrates.
right, and the vasa-recta get the water out of your way too.
Right.
So
And
here's
it shunts water from the descending to the ascending.
right.
Yep.
So here's another figure from this paper that shows again why the kidney looks like a kidney. I mean, it really shows that kidney looks like a kidney because it has to, because it's trying to do this. And then here I can't really see this but it's color coded. So and I can see that this is a long loop nephron. There's a short loop nephron, and they're trying to make some point here. What point are they trying to make?
Oh, let me see what they're trying to make.
Yeah.
I'm looking here. Okay, so they have a bundle, an interbundle, and then they have an intercluster and a cluster. They're showing aquaporin positivity in thin limbs
Yeah.
versus aquaporin negativity in the thin limbs. They're just doing the same
They're
kind
doing
of
it-
thing.
Yeah.
And they're showing us again the loop and how the aquaporin, is distributed.
Right. I think they're trying to make the point that again, think about these as clusters. Something's either in a cluster or between a cluster.
I see.
And I think that they're trying to say that we have to think about these things a little bit differently. It's not just one compartment.
Right. Okay.
So I think it's just an interesting concept.
Yep.
Now here is an ultrasection of that kangaroo rat. I think the kangaroo rat, which is the one that can get down to the 9,000. So again, center of the show,
Cortical
cortical
collecting
collecting, and look at everybody around the periphery. There's
Ascending.
the ascending
Then-
tubules.
Yep.
And the ascending
vasa-recta.
vasa-recta, and they're just hugging
And
this
X
thing.
marks the spot for the interstitium.
Yeah, X marks the spot for the interstitium. So again, this is where countercurrent is going on, as you pointed out. The flow coming out of here is coming toward us. Let's just say,
Right.
and that means if this collecting duct flow is coming toward us, this flow is going away from us. That's countercurrent, and there's this slight, small but real interstitial buffer zone.
Right.
Where all the driving forces are being put in, and so it's just a beautiful system.
Yeah, it's amazing.
And so this kind of takes us toward the end. Here's the confocal reconstruct, or the confocal slice that shows essentially the same thing.
Except this one is nice because it does show the collecting duct surrounded by all the ascending pieces, the ascending vasa-recta, the ascending thin limb, but then you have the descending thin limb kind of like one space away.
Right. It's not the immediate neighbor.
Right.
And so again, it slices like this, the 30 micron scale bar. It slices like this that you then reconstruct to make that.
Yeah, that is a great picture.
And this is, so I think, I tried to show enough pictures from a couple different groups to try to say, some of these differences are going to be species differences. Some of these differences are going to be preparation methods difference, methodology. But it's all, I think, when I try to go to sleep at night, I said, well,
I
maybe
haven't
I'll
been
think
able
about,
to sleep
maybe
since
I'll
we
think,
started
right.
this.
I said, maybe I'll think about the way the inner medulla looks, and then I find I'm never going to fall asleep. I think about this. It's not boring enough.
Oh, that's so funny.
So again, that's where we're going to. So coming back to it, that's where our animation took us, which was the right idea to the first degree, and then the nuances are added in. Here's pictures you might see in a textbook where you have to show still pictures, and again, still pictures don't do it justice.
Not at all.
Because there's, by definition,
there's so much complexity.
There's a lot of flow.
There's a lot of flow.
And the pictures don't move. So here again, the reason I came up with this, and it's wrong because as you already see, I'm already outdated.
Yeah, you got to get rid of those two bottom water ones.
I got to get rid of some of this.
Those two.
Yeah, I got to get rid of some of those. Right. So, but the point it's making is that water is coming out here. Just for the review, water is coming out here. It starts here. The single effect is here. The active transport. It starts here. There's this interstitial buffer zone. Water permeability here. The tip is half and half urea and sodium chloride. And the recycling, it's all done for this guy, the collecting duct. And the recycling of urea makes the urea gradient one direction, favoring urea going into the tubule, whereas sodium can come out by passive transport. So there's passive transport, and some of this is passive, and then some of this is active. Yep. So let me just end by showing you something and figuring out, this is my favorite movie. It's one of my favorite movies. The Nutty Professor, I think I'm going to show this for two reasons. One, Nutty Professor.
We love Jerry Lewis.
We love Jerry Lewis. But the Nutty Professor, and in the Nutty Professor, Jerry Lewis created what I think is the greatest comedy character of all time. They created the Dr. Jekyll and Mr. Hyde of Professor Kelp, who's the sweet guy.
Yeah.
Okay, he's Dr. Jekyll. And then the evil Buddy Love, who's his alter ego, and he takes the poison, he takes the stuff. But the reason I'm showing this is because my grandmother took me to see the Nutty Professor in Chicago when I was 6 years old. It came out in 1963, and I was 6. And my grandmother always took me to the theater a couple times a year. And this movie changed my life, because this movie, when I left this movie, I told my grandmother 3 things. She goes, how do you like the movie? I go, it's hilarious. I loved it. But it changed my life because I said, I want to be, this movie showed me, you could be a scientist, doctory scientist, and a comedian at the same time. And I said, I want to be a doctory scientist and a comedian.
You are the Nutty Professor, Alan.
Right.
It's perfect.
So in this one scene, the love interest is Stella Stevens, and you see the professor. And I'm going to play this, and people will focus on different parts of this scene. The part I focus on may not be the part you focus on. Let's play it.
See.
Let's play it once here. Let's see if I can get it to play.
All right, here it comes.
So it's not with sound. So he's smitten with her.
Yes.
And he's still a man, even though you see that I love the blackboard. It's got all the equations on there. And now she's Edith Head did the costumes. The great Edith Head.
Her outfits.
She did the outfits.
Changing.
Outfits are changing. First, she sees her in this gown, and she's gorgeous, and he's starting to react. This is all his head. It's not really happening.
Right.
It's all in his head, and the makeup is fantastic. And now she's the tennis player, and she's seeing that the evening formal wear, and then the tennis, and then now they're going to have another dance. Now there'll be something else, and he's thinking what's going on now, and now they're going out dancing. Okay, and everybody's focusing on this, I would assume.
Right.
Okay, but I'm going to play it one more time and show you what I'm focusing on.
Okay.
He's now she's really interested because
She's in the
bathing
swimsuit.
suit. She's in the bathing suit. She's gorgeous, Stella
Right.
Stevens. She was just great, and they loved working together. And Jerry Lewis always said she was the greatest, one of the greatest actresses he's ever worked with.
Great.
And now he's having trouble, like,
Yeah, right.
and now she's back, and they made her in this boring thing that was on purpose.
Right.
But now I'm going to play it again and show you what I focus on. So I focus on the kids coming in. So there's this endless parade.
I was looking at the equations.
The equations. But there's this endless parade of kids coming in. I'm going to make you notice one guy. So watch this. So you notice how they're all turning their faces away toward the door.
Yeah.
That's so that you won't recognize them.
Right.
Because watch this. You see, there's going to be this guy coming, a big guy, big guy with the book. Watch how many times these are the same kids.
Right.
Just in a loop.
Cycling through.
The same kids cycling through. We've seen big guy once. There's big guy again. Okay. And, you're paying attention to this. Some people are paying attention. I'm looking at this urea recycling.
It's urea recycling.
Urea recycling.
That's funny.
Keeping, and he did it the same way. He didn't take a million people. He didn't take a million people.
Right. He used them over.
He just used them over and over again. Just rotate around.
You save on extras that way.
You save. So he used urea recycling to save money.
You got it.
He only had to pay them this finite number of people. And there he is again.
Yep.
So he's looped in 4 times
Classic.
at least, and so that's why I love that. I love that movie for so many reasons.
That is.
And
awesome.
I was thinking of urea recycling. And go somehow or other the Nutty Professor must have to do with this, and that's the scene. So I just
classic way.
Of course, I have the DVD. I've watched this movie 500 times.
Oh, I'm due actually. Now that the kids are home, I think I'm going to have to.
I know there's another version with Eddie Murphy, but for me,
it's actually very good.
Yeah, but for me, this is the one.
It's the original.
It's the original.
It's
and
the
the concept was great. And so I said, there's got to be some Nutty Professor part for CounterCurrent, and that's my part for that. So then to finish up here, let me just say a couple words about the airport analogy, now that you've seen the whole process.
Okay.
So if we say that the kidney is O'Hare Airport, that the heart is downtown Chicago, when people fly to the airport to get to the heart, so the veins will take you to the heart, and the arteries will take you away from the heart. So the Tri-State Tollway, which takes you from the city. I
always think of blood flow with vehicles because when you see the red lights leaving you,
exactly,
it always looks like flow.
So if the passengers are the solutes and
Right.
the Tri-State Tollway is the aorta going to you get the Tri-State to the exit to the airport, that's the renal artery. Right outside the airport's the glomerulus.
Okay.
Haven't done any concentrating yet.
Got it.
The terminal is the nephron. Now, the descending limb of Henle is where water is moved and you get more concentration.
Right.
That's the solutes being concentrated at the gate.
It's probably security, actually.
Right,
beginning.
security. And then people boarding the plane, I left off security. People boarding the plane, they're leaving the city. They're being secreted. They're leaving the city.
Mm-hmm.
People getting off the plane are they're the ascending limb of Henle, and they're being reabsorbed. And then the cars and buses are the transporters. Rows into the city represent the vasa-recta. And then these rear recycling hotel shuttles. And then, of course, for people that need to stay in the vicinity, the interstitium, that buffer interstitium is the airport hotels where you're keeping these people, because the buses keep shuttling people. The shuttle means to recycle.
That's it.
The bus leaves the hotel, takes people to the plane, takes people from the plane to the hotel.
It's a short circuit. They've traveled, but nothing has happened.
It's a passenger recycling, except they're different people.
That's right.
But they're different molecules of urea too.
Right.
So this is the last slide. Just shows again where we started from. Again, as you say, I made mistakes here because I think it's good that our talk, even though this slide is new,
it does.
Our talk alone tells me I've made a mistake.
Hey, that's how we advance.
So what are your final thoughts, Craig?
It was such an eye-opener going back and reviewing this, because you learn it to pass the exams. And for me, the process of going through my fellowship and, of course, being in the lab, I was focused on things, but not countercurrent exchange as much, because we were focused more on potassium
and channels
and important similarities with all of these things.
Right, driving forces and
forces, permeability, and flows. And flows. Yeah. And so, but this was really a good breakdown of the steps and the interplay. I learned so much about the vasa-recta. I learned a lot about the descending thin limb, which I didn't realize.
Right.
That
and I didn't realize
such heterogeneity.
I didn't realize Aquaporin 1 stopped.
Right, exactly.
I mean, before this, I would have told you, Aquaporin 1 to the tip. And so I think would you agree that this week you concentrated on this?
Yes, I concentrated a lot on this.
Right.
And I think
so the idea is to keep that from being diluted.
And I think one of the things I would
recycle the
say,
knowledge so that you can keep the concentration.
exactly. I loved the process of how we went over this, because of all the videos you watch, people want to learn something in 8 minutes, and they want an 8-minute understand something, so I know how this works.
Right.
And look, those videos are fine and they have their place. And this is the 8-minute version, this last slide, because it kind of summarizes things in one place.
Mm-hmm.
But the complexity of these topics and the work people
people did,
are
those beautiful
putting
pictures
into understanding this.
Yeah, beautiful pictures. Where this is where did it all come from? This is, again, you can look at the flower at the flower shop,
Right.
but that doesn't tell you about the
Germination of the
roots
seed
of the
and all the
tree
things.
and everything. Yeah, right.
Yeah.
So if you're interested in just saying, okay, what does the flower look like?
For I
if
think
you're
the
interested
people,
in where to come from.
Yeah, and the people who are really interested in learning about CounterCurrent and this process and what we know so far, this is a great review.
Right. So these processes exist in the real world, engineering and nature. But I think when all is said and done, who's in first place? I mean, who's always number one? We're always number one because we're number one.
Right.
When the kids were young, what do you have to do? I do number one. We are number one. Okay. And if there's a process going on, the kidney has probably figured out the best way to do it. It's been at it the longest.
Right.
And so this beautiful system, I mean, this is necessarily complex. It has to be. It's been just thousands and billions of years of evolution and changes. But boy, the kidney uses every tool in the toolbox, changing everything, the length of loops of Henle. And,
oh my God, the expression of channels.
The actual heterogeneity. And I'm going to take a hairpin, but I'm going to make it the best hairpin loop you've ever seen.
That's it.
And
I love it.
And we try to copy it kind of pathetically in our dialyzer.
Right.
Exactly. But we can't quite make it like it really is.
That's
so,
for sure.
I mean, I think both of us really enjoyed this. This is not a short talk.
No.
But, and since we're giving it, we're interested the whole way. But I think it's interesting. And if somebody really wants to say, look, I want to spend a little bit of time and really know who all the players are and dig in a little bit, know where to go for further study.
Right.
This is that presentation.
I would say.
Yeah.
So listen, I want to thank you, Alan. That was an awesome review, and you did a great job, and I really appreciate it. And I loved going back and
we have to figure out
this
what's
stuff in more
next.
deep.
We have to figure out what's next.
We do. What do you think?
Well, it could be diuretic, could be genetics of.
I think diuretics lend themselves to this.
No,
yeah, so I think that sounds good.
What?
Awesome.
Thanks, Fred.
You got it, Alan. Take care.
Happy New Year.
To you too. 2022.